Hello, and welcome to this recorded webinar on load calculations for sizing heat pumps in Colorado. Now, this is part one of two free heat pump trainings brought to you by Energy Smart Colorado in partnership with Xcel Energy, La Plata Electric Association, Platte River Power Authority's Efficiency Works program, Holy Cross Energy, and the Beneficial Electrification League of Colorado, otherwise known as BELCO. As we get going, I'm going to turn off my camera here just to ensure we've got enough bandwidth for this recording to hold true. So we'll be back in one moment with our next slide. So here we are. This is where we are today. We are about to jump into this content. Remember, there are two free online webinars here that have been recorded. Today, we're going to talk about the importance of sizing and right sizing the equipment and calculating the loads. We're really going to focus on the load calculation, but a bit on why it's so important to get right sizing correct. We will talk about how weatherization can affect load calculations. We'll go through the fundamentals of load calculations, and we'll talk about some of the tools for load calculations that are available for you today. A quick tale of two CEEs. In the promotion for this, it was mentioned that I'm Dan Wildenhouse from the Consortium for Energy Efficiency, but actually I'm Dan from Center for Energy and Environment. And this is a fairly common misconception in the industry. It's quite all right if folks get it wrong. Happens all the time. The biggest difference is the Consortium for Energy Efficiency is a relatively small organization with a large footprint. We're talking somewhere between 15 to 25 employees, but they work nationally and even internationally, working with folks from Canada. The consortium's job and their goal is to represent their members, who are most often utilities, programs, and governments, to help create specifications, standards, and processes to look for energy efficiency. Now, you are probably most familiar with them in the residential sector because they're associated with what's called the 25C tax credit. This is a federal tax credit associated with weatherization, HVAC upgrades, and the Consortium for Energy Efficiency helps to develop the standards and specifications that those 25C tax credits will be measured against. The Center for Energy and Environment, on the other hand, where I work, is a much larger organization, still manageable, between 200 and 250 employees, primarily located in Minnesota, although I'm located in Colorado, and we have folks across the country. We work primarily in the upper Midwest as well as the Northeast and the Northwest, but we have been expanding across the Great Plains and the lower Midwest as well. We run programs. We actually have a lending program in the state of Minnesota, and we do a lot of research, primarily field research and data analysis. Our goals at the Center for Energy and Environment are to take this degree of research and bring it into pilots and programs and specifications so that folks that work with us understand that our data has typically been field tested either by ourselves and partners, or sometimes even by our competition. And that is something that we embrace at Center for Energy and Environment, is data that leads to program design that we know will work. So here I am. I'm Dan Wildenhouse. This was me pro-mustache. You'll catch me out and about at a lot of conferences and events, sometimes with the stash, sometimes without. I am a senior technical manager and lead trainer at the Center for Energy and Environment. And I sometimes joke I'm a recovering contractor because I did spend the first 15 years of my career actually working in the field, trying to fix homes and help build new construction homes. So I worked as a contractor doing HVAC, some installation, a lot of repair work, a lot of weatherization, just about every component of weatherization you can imagine, home energy rating in new construction, and even a little light drywall and framing. Now, I was terrible at the drywall part, so they usually sent me over to the insulation crew in those days. But after about 15 years, due to a combination of a downturn in the economy and some health challenges, I realized probably spending most of my days in crawl spaces and attics was not going to keep me in the industry for a long time. It just so happened at that time that there was something called the ERA funding. It's similar to the IRA funding that we have now. It came from the federal government, But unlike IRA funding, there wasn't a lot of money for incentives. Instead, it was all focused on training and development. So I worked for some community colleges, not to mention some program implementation firms, doing training all around Oregon and Washington primarily, and then eventually through Montana and Idaho as well in those days. And I parlayed that into a nice last 15 years of my life as a career, working as a trainer and a consultant for program implementation companies. As I mentioned, I am a Colorado resident, so when I talk about cold climates, I somewhat know what I'm talking about. I've also spent a lot of time in the Pacific Northwest, and I was actually born in Ohio. So I'm a Midwest raised, Northwest grown up, now Colorado resident, working all across the United States. At CEE, you can learn a lot more about us if you either want to go to www.mncee.org, or you can take out your phone right now and you can click on that little QR code, and that will take you directly to our website. Again, we do a lot of technical trainings and pilot and program development, typically, again, based off of research. We do design and implementation, equity and income qualified programs. We do run commercial programs, multifamily residential. We're very well versed in energy advising and customer experience journeys. And in Colorado, we've worked with the City and County of Denver, Platte River Power Authority, Xcel Energy, Gunnison County, Belco, and Energy Smart Colorado. So feel free to learn more about what CEE brings to the table. But with that, I want to jump into our content here pretty quickly after I introduce my Colorado coworkers. So if you're working with us in Colorado, again, I'm the one on the right, Dan Wildenhouse, but you may also encounter Gabrielle Bree Rink. She's our program implementation manager here. She's down in Colorado Springs, and she helps implement and deliver all of our programs and pilots across the state of Colorado. And then Robin is an energy advisor with a specialty in electrification. She's based in Englewood, just outside of Denver proper, and she works with equity priority commercial building owners, contractors, and community-based organizations to advance electrification. So you can see we're trying to be well-rounded here. We are growing, but at a slow pace in Colorado. Our goal is to fit in where others are not currently delivering. So our hope is that we make a round and robust set of opportunities for folks who want to advance energy efficiency, decarbonization, and electrification across the state. A little bit more details on what we're going to cover today. I did mention this earlier, why load calculations matter, the fundamentals, weatherization impacts, the tools. We'll do a summary. Now this was originally a recorded webinar, so we don't need to worry about you using the chat function here. This is just a straight recording. We won't have to take the breaks, and there's not going to be a Q&A session. What I'll try to do is factor in some of the things that were brought up when we originally delivered things that were brought up as questions, and we'll address them as we go through. So with all this, hopefully we'll come in a little under 2 hours for today for this webinar, and the same should be true for the next one that we do on Manual S, or sizing and selection. So why are load calculations and proper sizing so important? We find it's really good to do a little bit of level setting early on in a training like this. What we really want to do is get everyone on the same page with what we consider the problem statements to be, and then we can build towards some goals of the training. So what's the worst that can happen? Okay, so these things are magical, right? Heat pumps, magical creatures. They supposedly can vary their output to match what's needed in the home. So really, is it that big of a deal if I undersize or oversize this equipment? Well, undersized systems, this is where there really could be a problem, but the good news, this is extremely rare. We'll get to why it's extremely rare in just a little bit. But why would it be important if you undersize your system? Well, if you undersize by 95% of the heating load or lower, you do run the risk of the system not being able to heat the home during the coldest parts of the winter. And nobody wants a brand new system installed that cannot heat the home. We also don't want it to not be able to cool the entire home during the hottest parts of the summer. right? People invest a fair amount of money in a brand new heat pump. We want to ensure that during the cold parts of the winter and the hot parts of the summer, the system is doing its job. We also may need to run for long periods of time at full power and full speed if we're undersized. Where we get our most efficiency with heat pumps is it being able to run for long periods of time at part power or partial speed, typically somewhere between 1/4 and 60% of the capability of the equipment. When it can run long periods of time in that range, that's when we get the maximum efficiency. So these undersized systems, if and when they happen, they tend to not be able to heat, not be able to cool the whole house, and they're spending a lot of time running at maximum power and speed trying to keep up. So you don't have the efficiency and you don't have the comfort. What about the flip side though? What about when we oversize systems? And spoiler alert, this happens a lot. Oversized systems, everything I'm going to name off here, you can see on the screen, are very common experiences that homeowners will share, probably even with their current system. So short cycling, turning on and off a lot, that's pretty common. You've probably seen this happen or heard this complaint from a homeowner before. My darn thing just doesn't seem to stop coming on and off. That can lead to poor distribution. So our ductwork designs, inducted systems, or actually in hydronic systems with piping going through the house, or even ductless systems, they really depend on the right amount of runtime. So if it's on and off and on and off, you're just not going to get that distribution. It can be really hard on the equipment. Coming on and coming off, those are high power using times, so they're not able to run at their most efficient. And those hard stops and starts can be the most challenging part of your system. And it can be really annoying to the people who live in these homes. Again, it's one of the top complaints we get, is that this thing, can't keep the upstairs cool or the downstairs hot, and that it's annoying that the thing comes on and off a lot. Now, it can also cause excess fan energy use. Now, there are several different fans involved here. I'm talking about the air handler fan. So that central fan, typically it's in the same box as either the gas furnace or the heat pump, depending on what type of system you've purchased. But that central air handler fan, when these things are oversized, modern ones have what are called electrically commutated motors. And what ends up happening, or an ECM, what happens with an ECM is when it's trying to push through an undersized ductwork compared to the size of the system, so an oversized system for the right size ductwork, it's going to encounter static pressure. Now, static pressure in ductwork is the pressure trying to go outward everywhere, which is different from velocity pressure, which is trying to push it down the ductwork. The static pressure is the part that's kind of, if you imagine a balloon that you've blown up, it's the pressure on equal range on all the way around that balloon. That's your static pressure. When you have increased static pressure, the electrically commutated motors, those ECM fans, are going to work as hard as they can to still try to deliver the air throughout the home. As they try to deliver that air throughout with that higher static pressure, they will ramp up and use more energy. So causing excess fan energy use can be a real problem, and that leads to this next one, could be oversized for the ductwork. So oversized for the ductwork can lead to high static pressure and excess fan energy use for ECM motors. For non-ECM motors, for older systems, what we call PSC motors or permanent split capacitor motors, when you're oversized for the ductwork there and you get high static pressure, it doesn't increase your fan energy use so much as it lowers your ability to distribute the air throughout the home. What I'm talking about here is PSC motors have a different set of problems when they're high static pressure. They are not designed to ramp up and deliver the air. Instead, they will continue the same amount of power usage, and they simply won't move as much air. So that can be a real problem. Now, a question we got when we did this live is, Dan, when would I expect to know that difference between a ECM and a PSC motor? And there's a couple different components to this. First is that ECM is a very general statement. There are a lot of different kinds of motors that are generally put in the ECM category. There's the X13s, which are actually constant torque motors. They're technically not a true electrically commutated motor like an ECM 2.4 or higher. So that's one thing to understand. Constant torque motors are a little bit different than true ECMs, but the biggest thing is they're not a permanent split capacitor motor. The second thing is that about when did this changeover happen? And I believe it was 2017 is when they were no longer allowed to be made. So this is because the federal appliance standards that the DOE and some other federal agencies help manage went live in 2017, and essentially distributors had until 2019 to sell off any of the equipment that had been already under construction. So effectively, if you bought a piece of equipment anytime from 2019 and later, a central air handler system should have an ECM motor or ECM fan as a component of it. So it'll either be an X13 or the ECM 2.4 or higher systems. That again, anytime after 2017, it's very likely. After 2019, it's almost assured. So just trying to help bring that up. That was a decent conversation we got when we did this presentation live. The next component of this, this is some research that we at CE had done back in 2017. And this was actually for some boiler systems, but really what we were looking at were the load calculations for these buildings. Now, I wanted to bring this up because this is part of that thing of how do we know that systems are oversized, and what about, didn't I just hint that you could get a system that's only 95% of the load and probably still do the job? Well, here's why we believe that that's true, and here's how we know that current systems are oversized. This was as a part of this research that we did. We were looking at all of these different systems, and we had two contractors, contractor A and contractor B, each do a heat load calculation for the home. Now, we did not dictate which tool they used. We did not dictate the parameters or minimum requirements. We just let them know we would be essentially grading their homework, right? We'd be looking at their manual J's. We also monitored and measured the actual energy use of these homes during the days and nights that most closely aligned with the winter design temperature and the summer design temperature. That's important to understand because that's not necessarily the same as the coldest or hottest day of the year. But at any rate, we tried to do the monitoring and measuring, and so when you look at this graph here, I apologize for any of you who are colorblind because I know that these colors are hard to read for that group, so I'm going to read them left to right, and I'll also mention the colors. So for each site, you see those numbers at the bottom, 1062, 1055, 1028. Each of those is a site, meaning a house with a system in it. Within each site, there are 3 bars. The one on the left, for those of you who are not colorblind, it's gray and it's got the little black eye on top of it. That's the actual monitored and measured energy use during those cold times, right? The center one, which is red for those of you not colorblind, is going to be contractor A, and then the green one will be contractor B. That's the one on the far right. So you'll notice a few things right off the bat. One, on site 1049, for some reason, contractor A did not submit a load calculation, so we only have contractor B's effort there. Second, you'll notice that contractor A and contractor B often, almost always in fact, got very different numbers. Only a few of the houses, 1055 and 1031, were they effectively getting the same heat load. Now, just because the numbers were different doesn't mean the end of the world. If you look at 1062, contractor A got 47,000 BTU per hour, and contractor B got 40,000. Well, guess what? That's both of them are going to recommend a 4-ton heat pump, right? Because 48,000 is the next logical step up. So it doesn't really matter that they were slightly different. It only matters when they were dramatically different. But speaking of dramatically different, the other thing you'll probably notice here is that the gray bar, or the bar on the left, compared to the two bars that were modeled, is radically different. In many cases, it's half the amount that was modeled. Now, even if I just look at this area that I put a box around, these are the larger loads. And again, these are all homes in Minnesota. So we're actually talking real homes in cold climates. Even if I looked here, we're still seeing some of the homes being very modeled a lot higher than the actual monitored and measured energy use. Now, as you get to sites 1031, 1063, and 1045, you are getting closer sometimes, not always. If you look at contractor A for site 1063, still very different. So what is this telling us? Telling me a couple of things. Contractor A and contractor B could have been using slightly different software. They could have been using different standard inputs. So in other words, they could have said, well, we didn't do a blower door test, so one of them may assume that the homes are average in their leakiness. The other person may assume that they're somewhat leaky as a standard. Those kind of things, which we did not have the ability to check, must be happening because we're getting these different numbers. And we are getting much higher numbers modeled than we were measured. So if you did 95% of that modeled load, and that's what you actually assumed and installed a piece of equipment to, in probably every case except for maybe 1031, you'd still have enough bandwidth in there. So that tells me that not all contractors will get the same answer in terms of absolute BTU per hour, but they're probably going to come very close in recommending the size of equipment if they're actually doing repeatable and relatable and recognizable manual J calculations. When they do that regularly, they're usually going to come within, again, one size of each other in terms of the heat pump they recommend. And two, there is no need to do any extra thumb on the scale when doing manual J, because the monitored and measured loads of these homes, even in very cold climates, is still quite a bit lower than the modeled numbers. So adding any extra oomph to your heat load calculations is completely unnecessary. And it's not just CEE saying this. It's not just our results from that one. Anyone want to take a wild guess who said this, right? Manual J should take full advantage of legitimate opportunities to minimize the size of estimated loads. Again, minimize the size of estimated loads. Applying an arbitrary safety factor is indefensible. No additional safety factors are required. This is actually from ACCA Manual J version 8, which is the current version that is out. Now, Manual J is going through an update process starting, I believe, here in 2025. So by 2026, 2027, we may have a new version of Manual J available. But this just goes to show that even ACCA themselves agrees there is no reason to add additional safety factors. This is already incorporated into the estimation software. How about some of these other quotes? We need to stop arguing about the length of the haircut and discuss whether or not to shave the head. Well, first of all, what the heck does that mean? Well, it means that there are some minor differences that are not worth arguing about. Was the wall blown to R13 or R15? Nah, it doesn't really matter. What matters is there insulation in the wall, yes or no? And this is from Russ King. He's a great HVAC trainer and legend in the industry. He's the inventor of Quick Model 3D. I may have butchered his quote a little bit, but you get the gist of it here. And Russ is like the rest of us. He understands that this isn't about perfection. This is about getting those reasonable and repeatable results that we can rely on. Next up, 125 to 140% of the design heating load is reasonable to expect when we're looking at existing equipment. So who said that? Well, that's from Natural Resources Canada in their air source heat pump sizing and selection guide. So they've looked at this, and they've looked at thousands of homes across Canada, and what they've found is that it's really, really common, even in the best case scenario, for systems to be 125 to 140% of the design load. Not the end of the world at 125%, but you start getting to 140%, and we start getting to the problematic. So this is with those that were actually using something like Manual J. And then from DOE and their right sizing heating and cooling equipment technical fact sheet, they mentioned that a large-scale study or survey where 40% of contractors indicated that they purposely oversize equipment, trying to reduce callbacks. So what we've got is data that shows that our load calculation estimates are higher than modeled and measured. We know that we need to focus on getting that repeatable and reasonable data entry, good quality data, like Russ is mentioning. We know that up in Canada, they've said, hey, even when they're doing load calculations, they're probably 125 to 140% over that. And we know that around 40% of contractors indicate that they're purposely oversizing equipment or pumping up the loads. When we add all this up, this is that indication. This is why we said earlier, very rare and seldom are systems undersized and very commonly oversized. We can address each of these, and we're going to try to throughout the rest of this session by talking about making sure we get quality data entry, making the differentiation of what's worth worrying about, that R13 versus R15 in the wall, or the R13 versus R0 in the wall. And then we're going to look at the different types of load calculations and whether or not we think they've got this flexibility to over 140% or more, because there's a bunch of different ways to do load calculations, and we want to make sure that we're doing, again, the things that are somewhat reliable, repeatable, and produce reasonable results. So let's wrap all this up into our problem statement here. Sizing, design, and selection is often done solely based on rules of thumb or on previously sized systems. This is what we're finding over and over and over again, and you just saw the results of when we do this. We find our systems are very much oversized. People are not doing good data entry, and we're not getting very reasonable results. And variable capacity air source heat pumps perform their best and meet the savings goals when they're sized appropriately for the system type, the application, and the supplemental fuel type. We'll get into this a lot more, but this is the goal, right? This is when they work their best, so we want to get that appropriate sizing for the system type, the application, and the supplemental fuel type. So is it a big difference to size for heating versus size for cooling? Are ducted systems and ductless systems different? Are cold climate systems versus not cold climate systems different? And do we want to pay a different level of attention if our supplemental or backup heat is natural gas versus if it's propane, home heating oil, or electric resistance? I'm here to tell you I think each of those different statements can make a difference in how accurate we feel we need to be. But all of this goes to say that if we want our variable capacity heat pumps to perform their best, we need to factor all of that stuff in to our sizing and our design, and load calculations is where we start. So I believe this to be true. All new systems should have some type of load calculation performed. What you see on the screen here, again, sorry for those that are colorblind, but we tried to color code this to indicate the difference between things we don't really like and things we do like. But a different way to say it is the level of load calculation, time and effort required does tend to align often with the quality of the output. Now this is changing. I should say level of load calculation time and effort or cost is correlated, because for a fairly low amount of time and effort, we can just shoot from the hip, like just say, I've been in 1,000 homes, I know what these homes need, I'm just going to do it. Now, you might be fairly accurate, but it's not going to be very repeatable or very reasonable if you're training other people to shoot from the hip, because everyone will have a different set of experiences. Sizing off the existing equipment and using rules of thumb, particularly antiquated rules of thumb, those are ways that you can do a load calculation with very little time and very little effort. What all three of those have in common, they're not likely to be very accurate or reasonable, and they'll probably not be very repeatable. Now you can upgrade to a medium-high amount of time and effort, and you should be getting a medium-high degree of reasonableness and repeatability with your load calculations. So a block load calculation definitely falls in this category. So this is where we look at the total heating and cooling load for the entire home or per floor, as opposed to doing it for each room. So it saves us a little time, and it's fairly accurate. There are times where you want to do room by room. We'll get into that a little bit more a little later, over block load. But for most existing homes, unless there's a serious IAQ or a comfort problem, the block load is that right balance between medium high reasonableness, also medium high time and effort. There are some other things, like you can get a little bit higher quality by using runtime or utility bills, but it may take you more time and effort to do it because you may need multiple years of data. You may have to collect that data, graph it out yourself, right? Some of this stuff is pretty easy to do. Some of it can be a little more challenging. And then we're going to move from that to the high category. So it takes the most time and effort, or maybe you found a way to do it quickly. In that case, it may take more money, but you get very high quality, repeatable, and reasonable results. So this is where room by room manual J are equivalent, and it does require very detailed envelope information and very detailed measurements of the home. So again, all of these are possible. We really like the medium, high, and high in terms of what we feel is a responsible way to handle this. So, does this sizing really matter? This is the first question I get is, Dan, is there actually any energy penalty for oversizing our equipment? You talked earlier about the ductwork, okay, the annoyance of the thing coming on and off. Is there really an energy penalty? So there's a lot of research out there. Very little of it, however, is really specifically focused on answering these questions. So what I had to do is pull out some data from several of these, from NIST, NREL, Procter Engineering, and IIT. Each of these had different kinds of data sets looking at something different, and all hinted towards this. So the first thing that we found is if you oversize by cooling for the cooling load by more than 140%, you're likely to get some energy increase in your system. Now, that could be somewhere in the 2 to 9% range, right? It's probably not, for most systems, going to be much bigger of a penalty than that. And I'm talking about the energy to run the compressor, right? Not the air handler fan. We'll get to that in a minute. For heating, very similar, a little bit more flexibility. If you oversize by more than 150%, you're likely to see some energy increase. And this is, again, probably somewhere in the 1 to 7% range. So there can be some small energy penalties here. It might only add up to 2 or 3%, or it might add up to 15 or 16%. So it's measurable. It's enough to notice, but it's probably not the be-all, end-all in terms of energy penalty. That's on the compressor side. However, if we oversize incorrectly for the ductwork, so either the ductwork is undersized or the equipment is oversized for the ductwork, especially with the electrically commutated motors, or ECM fans, we have a higher fan watt draw. So again, trying to push that air through the ductwork, that resistance is building up. The fan tries harder and harder. We're going to get most of our flow with an ECM, but our fan power can go up by almost 50%. So that means instead of using 300 watts to move the air, it might be using 450 watts, right? Now that, with long run times, really can add up. So we might get those small energy increases on the compressor side for oversizing for cooling or oversizing for heating, but we really can get a really big number if our compressor in our system is dramatically oversized for our ductwork. Don't worry, we'll cover that a lot more in our second of our 2 sessions. So what other real-world challenges may exist when we oversize, right? It's not always just about fan energy. There are other things that matter quite a bit here. For filtration, if you have invested in decent quality filters for your system, Maybe you do it because of wood smoke, right? You want to help reduce the impacts of wood smoke in the home. Maybe it's in response to the pandemic and people both spending more time in their homes. Maybe they teach their kids there, they work from home, they work out at home, they go out to eat less, and they're a little more concerned about airborne issues. Filtration will matter. So let me ask you this. Does the filter do anything if no air is moving through it? No, of course not. So we want to have good run times. Now, somebody said earlier, Dan, what do you mean by a good, what's an example of a good long run time for a heat pump? During peak cooling season and peak heating season, we'd like to see that thing running about 100, 90 to 100% of each hour. That's honestly what we'd really like to get. So around 55 minutes per hour would be ideal. That, as long as it's not at full speed to do that. If we can be running like that, and most of the time is, half speed, half power, with some ramping up, that's fine for 55. Then during the rest of the year, what we call our shoulder seasons, or during the warmest part of a cold day or the coolest part of a warm day, if it dips down to 30 minutes, that's probably just fine. What we want to avoid are under 30-minute run times. That's where we get our problems. For ventilation, just like with filtration, if we're either integrated, meaning a duct from an HRV, ERV, or a fresh air duct is coming into our system, or if we've just using our control strategy to control a separate ventilation system at the same time that we control our central air handler, guess what? If that air handler is not running, then neither is our ventilation. For home destratification, now particularly at those homes where the top floor is 6 or 7 degrees warmer than the main floor during the middle of the summer, and in the winter the basement is 5 to 8 degrees cooler, or maybe little Susie's bedroom facing southwest is always hot and is hard to get ever cool, or maybe your home office in the northwest corner really never warms up as much. We can address this stratified air through a lot of air mixing. And in order to do that, we need that fan to be running a fair amount of the time. On and off systems can lead to larger temperature swings. So they're depending on the quality of the thermostat as well as some of the settings that are built into them. This can mean that the system satisfies the thermostat but keeps heating for a couple degrees, so it overshoots your thermostat by 2 or 3 degrees, and then the room starts to cool down, or the house does, and it doesn't come on again until it's 2 or 3 degrees below the thermostat set point. That can happen, and these oversized systems can have these dramatic temperature swings by as much as 5 or 6 degrees in the house, just trying to maintain. Now, a system that runs the majority of the time may only have a 1 or 2 degree temperature swing. So you tell me, what do you think most customers want? A 1 to 2 degree temperature swing or a 5 to 7 degree temperature swing? I think you know the answer. If we're trying to, in Colorado, add humidity to our home, so we could actually be using something like a steam humidifier that we connect to our central system, or maybe we have standalone humidifiers in parts of the house and we're relying on that central air handler to move that air around. Guess what? If you want that to have more even humidity distribution throughout the home, you need to have that long run time. Now, if you're watching this and you're not in Colorado, you're in a more upper Midwest state, it could be the flip side. It could be dehumidification. Same challenge. If you are trying to use dehumidification, either the air conditioner function or an external dehumidifier, same thing happens. We need to have these run times to make it work. I'm not going to get into it in these sessions, but when we do specific training in the Midwest, there's a lot more that we focus on for dehumidification because there are some additional challenges beyond just runtime that we focus on. These larger compressors and fans may require larger electrical circuits. So it's another question I get asked all the time. Dan, if we're moving to heat pumps, one of the challenges is going to be, aren't we going to require then a lot more of our homes that only had a central AC or maybe didn't have, only had portable ACs aren't we going to need all of these to upgrade their electric panels and some of their connections? Well, maybe, maybe not. There are a lot of different ways to do that. We have a whole separate training just on that. But a larger compressor and a larger air handler fan is likely going to have more peak energy and therefore require a larger electrical circuit. So right sizing our equipment is a great way to protect and reduce the number of times we need to do electrical work on the home in order to adopt a heat pump. Larger compressors and fans are also sometimes noisier, particularly when you get to the 4, 4.5, and 5 ton range. So the upper end of our split system heat pumps. And boy, nowadays with putting these things in, we have homeowners associations, we have cities and local governments, we've got utilities, all with different rules about where outdoor compressors can go, how close they need to be to an electrical switch or shutoff, how close they can be to a neighbor's property line, whether or not they can be seen or heard from the street. Because of all this, we get these restrictions, and we end up being able to only put these outdoor compressors in a few locations. And it might be unfortunately underneath a window or next to the back deck where we want to barbecue all summer. And we just don't want really large, loud systems put into places that might be a little unfortunate in terms of our ability to hear them. So we really want to think this stuff through. Larger compressors can be noisier. Let's go for the smaller compressor with long, consistent run times. That will hopefully lower our noise the most. And then again, I keep mentioning this because it's so important. These oversized systems can struggle with the existing ductwork. It is an important part. We will get into this more in the second of these 2 recorded seminars. So next up, we want to look at some of these system sizing done by rules of thumb. So we talked a lot so far about why it's so important. So now we're going to show some rules of thumb. Now some of these are real and some of these are kind of jokes, but they all get to the same point. I could leave it to you to determine which ones you think are real and which ones are jokes, or I can call it out for you, but they're all equally potentially inaccurate. So the first thing you see here, now this is kind of a joke, but I was actually trained at something very similar in my youth. So the idea here with this sizing chart is you would cut out these 3 houses, then you would stand across the street on the curb, and you'd hold up the piece of paper, and whichever of those cut out houses most closely matched the house you were looking at, that would be how you would size your system. Now obviously that's a joke, but we were actually taught in the early 90s to hold up how many fingers does it take to block the house if I'm standing across the street. 1 finger, 1 ton. 2 fingers, 2, 3, 4, usually 4 or 5 tons. That is unfortunately not that uncommon way to do it. Something we've heard a lot on the eastern half of the United States is 1 ton per 400 square foot. Actually, I've heard this in a lot of places when it was air conditioners that they used for sizing, but in the eastern half of the United States, they just took this AC sizing factor and they applied it to heat pumps. So 1 ton per 400 square feet. That may work just fine in Nashville, Tennessee, for a home built in 1980. But an older home or a newer home, I don't think that would work. Is it going to work the same in Miami, Florida, or Austin, Texas, or Phoenix, Arizona? Right? Each of those are different types of hot climates, different types of humidity. At any rate, you can probably sense that that is not a universal truth. You can flip the script, and this is something that was done on the West Coast a lot, particularly and specifically sizing for heat pumps, and that would be 35 BTU per square foot. So a 2,000 square foot home, right? You could do the math. We would do this, and we would say that's how many BTUs we needed. Again, do you think a house in Seattle versus a house in Minneapolis versus a house in Aspen, Colorado, do you think they all have the same needs? So is that 35 BTU per square foot going to work out the same for everyone? Probably not. This one, I mean, this makes me laugh just looking at it. The tonnage is half the number of cylinders of the customer's biggest car or truck. Now, obviously this one's a joke, sort of. When you pull up to the house and all they have are very, very large vehicles, you probably will not be successful at smaller is better in terms of a sizing strategy, right? People do like stuff to be big. We're Americans, right? The biggest steak and the biggest baked potato I can get. That kind of mentality is true. It does exist. It's just something to be aware of. What's in the shop today? Now, this was actually not a joke during the pandemic, was it? This was, whatever you could get, that's what you were able to install. Yeah, I mean, the joke I would say is, looks like this summer everyone's getting a 3-ton, right? Because that's all we could find. So this is still true today. Now, it can be specific to your shop or your local distributor, but it can also be true with certain types of equipment. When we talk about coil-only matched equipment, so we're replacing a central air conditioner, but we're keeping the gas furnace as is. So we're going to replace the outdoor compressor and the indoor coil, but instead of doing it with another AC, we're going to put a two-way air conditioner, aka a heat pump, in there. And they sell these coil-only matches. Several brands are out there, but sometimes they're only sold in 3- and 5-ton increments. Now, you can do some ninja work with both control settings as well as, mismatching and on purpose the outdoor unit to the indoor unit. You have a 3-ton indoor, 4-ton or 5-ton outdoor, and kind of get close to a 4-ton in performance. Those types of things can be done. But what's in the shop today could mean, literally what's available to you from your distributor, or it could mean, hey, I'm trying to do a specific approach, and they're only sold in 3- and 5-ton. So all of that is true. A 1/2-ton bigger than their neighbor. This goes back to the give me the largest steak and the largest potato you got, sir, kind of mentality. But people do like to compare, right? Mrs. Kim and Mrs. Johnson are playing canasta on Saturday night, and Mrs. Kim says, "Oh, that's adorable. You got a 3-ton heat pump. Ours is a 3.5-ton, right?" People can't help themselves. Sometimes they like to do these comparisons. Wouldn't it be great if people instead did it the other way around and said, "Oh, I'm sorry, you paid extra for that 3.5-ton. We were able to get our 3-ton to do the work." That would be ideal. And then, of course, there's all these different rules of thumb. Particularly, there are some that you can find online that look kind of like, hey, this looks like someone has put some thought into it. But then you actually do the math, and it's quite ridiculous. So rules of thumb can be challenging. It doesn't mean that they don't have a place. It means they can be challenging. So rules of thumb online is a good example. So we try to want to avoid as much of this stuff as possible, and instead lean into things that, again, if we want that reasonable results, we have to take into account where the place is. So I mentioned earlier, Minneapolis, Minnesota is going to be very different from Seattle, Washington, which is going to be different from Fort Collins, Colorado, which will be different from Nashville, Tennessee. So where it's at, how big the house is, that's going to matter, right? A 3,000 square foot house and a 1,500 square foot house will simply need different amounts of heat. And then how well air sealed and insulated is it, and where is the ductwork? If it's all ductwork in the basement and it's a fairly well insulated home, that's going to be very different than a 1910 really old house with very little insulation. It's very leaky, right? So each of those things need to be accounted for in some way, shape, or form. And that's the problem with anything that you see here. None of these address all of those concerns. So if we want repeatable and reasonable results, and I just mentioned a lot of the different data things that we talk about, well, we can think back to what my mom, who is a substitute teacher, and my mother would, just like any other grade school teacher would have said, you will only get out of it what you put into it. And she was talking the same about math tests as, asking a girl to the dance, right? If you put effort in and you put care in, you'll get better results out. So we want to think about the same thing when we talk about doing our load calculations. So this is a tool that I use quite a bit. It's called the HVAC sizing tool, or we sometimes call it HVAC Street because it's HVAC ST are the initials. There's a link at the bottom here. You are all getting PDFs Anyone who attended the seminar gets a PDF, but for those of you who just kind of found this online, you can just Google Better Built Northwest HVAC sizing tool. That will also work. We like this tool because it's relatively fast to enter information. You do need to have collected all the data, but you can do a block load or a room-by-room load calculation with this software. Now, I will warn you, this is not full ACCA approved. We'll get to more of that in a few minutes, but it does give pretty good, pretty reasonable, pretty good replicatable results. So here's our example house. We're going to use a fair amount today. It's a 1,600 square foot, 2-story home over a basement in Leadville, Colorado. Now, I picked Leadville because it's a very high elevation. It's also, you know, western slope / mountain area, so it's going to be it's going to have some pretty cold times. So very cold climate, very high elevation. I'm going to use this as an example because it's kind of on the extreme side. The home is built in the 50s here with ducts in the basement, and the systems are pretty old. So this is some of the important things we'll need to know going into the actual load calculation. So here's a load calculation tool I found online, right? This rule of thumb. Again, it looks kind of like, I don't know who ASM Air Conditioning is, but heck, they actually have a different range of BTU per square foot depending on where you're at. Okay, so they're doing that. They've got a different set of ranges for heating than they do for cooling. Okay, maybe that kind of makes sense. On the cooling, they actually have it, you know, different zones and square feet, right? Get into different classifications. So it feels a little bit like, it kind of looks like maybe this is legit. So let's do the estimate. That 1,600 square foot house, if I picked 55 BTU per square foot as an average for heating, that's looking at this, the left side of the two charts, right? Zone 5 is where, you know, the high elevation western slope of Colorado is, in that blue. So I picked 55 because it's the average between 50 and 60. And if I multiply that by 1,600, my heating load is 88,000 BTU per hour, which means I probably need to put in a 100,000 BTU gas furnace, or I might have to put in 2 heat pumps if I were to follow this rule of thumb. Now, if I looked at the right-hand chart, Leadville is right on that verge between the green and the blue. So I either need 2.5 or 3 tons. If I look here for the 1,600 square feet, right, somewhere in that range. So, I'm going to go ahead and I'll calculate both, 30,000 or 36,000. What I just did is I used an online rule of thumb that kind of looked legit, and I've got, boy, quite a difference, 100,000 BTU gas furnace and a 3-ton air conditioner. What would happen if I ran that same house through something more in-depth, and I actually took the care to record the data and took advantage of all of those components that I mentioned are necessary for load calc. So I enter it into my HVAC sizing tool. Now you see in the upper right-hand corner, this demo house Leadville, it says, you can almost kind of think of this like your scoreboard. As you start going through and entering data on each of these tabs, the site, the building, the rooms, etc., these numbers will change if you hit save every time. Because you're getting more and more details added, it gets more and more accurate. So here we start on the building slide, right? I've said it's an old 2x4 poorly insulated house with a basement. I've identified where the ducts are, 80% conditioned area, 10% attic, 10% unconditioned basement or crawl space. I've got the number of bedrooms, the size of the house, the average wall height, all on this one slide. So this is just helping me collect all the data. And I would go through and I would do the same for the rooms, the windows, the overrides, and the options. When I do that, I get this number in the upper right-hand corner. It's saying my heating load is 58,000 and my cooling load is 18,000. So was that oversized? Well, yeah, if I use that online calculator, it said I need 2.5 tons more of heating and 1 to 1.5 tons more of cooling. So that is unfortunately what we see happening a lot in our industry. People are either using an improper tool like that load calculation online calculator, or they're just sizing off of existing equipment, and we end up with systems that are not just 1 ton bigger. They're 1.5 tons to 2.5. I've even seen some that are 3 tons too large because the tools that were being used were quite inaccurate. And that is enough to show your energy penalties, the fan energy penalty, and all those other challenges with filtration and noise and humidification all become challenging when systems are this much oversized. So let's talk more specifically about actually doing load calculations specific to our Colorado climates. So I'm going to go through, I mentioned earlier, where it's at, the size it is, the insulation and air sealing values. I'm going to go through these a little bit more detailed here so you've got the right starting place for any of this type of work. So we'll start with what we call our design conditions. So these are determined by ASHRAE, the American Society for Heating, Refrigeration Engineers, ASHRAE, ASHRAE, and ASHRAE Handbook of Fundamentals is one of the quintessential books that you can ever have if you really want to get good at understanding how buildings operate and how heat transfers in buildings. I highly recommend the ASHRAE Handbook of Fundamentals. It has all the math needed, and all the math that is used for heat load calculations is in there. They also have a separate website called the ASHRAE Climatic Design Temperature site. A little bit later in here, I'll show you, there'll be a couple of links for this. It's what I use right here, and I'm looking up the design temperature. So I used Leadville and Pueblo here as two. Now Leadville, because obviously you saw my example for Leadville. Pueblo, I may choose to do an example there as well. The design temperature, by the way, is not the coldest or hottest day of the year necessarily. It's the winter design condition says it only gets colder than that temperature 0.4 to 1% of the time. So it's not the coldest. And by the way, winter design temperatures happen at night, right? Because you've got night sky radiation, meaning you're giving away heat to a dark sky. You also have the least amount of things turned on in the house in the middle of the night, and you don't have any solar gains. So you add all that up, and that is the winter design temperature. Now, why 0.4 to 1? It's because there are two numbers when you look at this, the 99% and the 99.6%. I'm okay with you using the 99.6%. That is the one time where I'm going to say you want to do a little bit of flexibility and try to protect yourself. I'm okay with that, but be aware of the fact that codes and permitting and program standards may require you to use the 99%. That's fine. I like the 99.6%, particularly in very cold and very hot climates. So in Leadville, my winter design condition, if I use the 99.6%, is -8 degrees. That means 99.6% of the time, it's -8 or warmer. Only 0.4% of the time is ever colder than that. And again, since we know we've got padding built into our Manual J, that's going to be just fine. If we flip the script, the summer design temperature, which is going to be the middle of the day when the sun is shining its most brilliant, and we're doing the most in our houses, that's going to be the hottest. That's when we need the most cooling. At least 99.6% of the time, it will be 74 degrees or cooler in Leadville. Now, Pueblo, it's not quite as cold in the winter, and it's a lot warmer in the summer. So just even though they're both in the state of Colorado, it just goes to show that you really do need to dial this in as close as you can, because boy, that is a pretty big set of difference here. Next is the design conditions, is the internal part, right? There are some internal design temperatures that are prescribed and then recommended flexible ranges. So the number one thing I would say is be realistic, interview and educate the homeowners. When we talk about what is the prescribed heating set point, according to the ASHRAE math and Manual J, prescribed is 70 degrees for heating and 75 degrees for cooling. Now, as you talk with homeowners, it's okay to really listen and learn from them about how do they like to keep their home. So maybe they don't need it to be 70 degrees. That might be okay with 69 to 72, anywhere in that range. That's probably fine as long as you record this number down and you let whomever know if you're submitting it for a code, if you are getting a permit for a program or submitting this through your program data. You need to be able to record this so that these are reflected and you're showing transparency and honesty. And you do need to educate the homeowner as well. Cooling prescribed is 75, flexible between 76 and 74. I actually do know people in Florida who have these very large, very expensive condos, and they're setting it to 69 or 70 degrees for cooling in the middle of the summer. So it's true. Some people want to live in a mausoleum. Most people, though, are going to be in those flexible ranges. Just make sure you're having this conversation with the homeowner and you're jotting down if you use anything other than the prescribed numbers. So using the ASHRAE lookup for your most accurate design temperatures, you can see down at the bottom, here's a link. If you're one of the people who registered or attended the webinar, then you will have gotten this. Otherwise, you can just Google ASHRAE design temperatures. You definitely want to click on the 2021. You want the most current, and you want IP, right? Inches and pounds versus scientific. Unless you're really good at translating Celsius to Fahrenheit, make sure you click on the IP. What you do is you zoom in on this map, and then you right-click. Sorry, those of you that are Macintosh users. You right-click on the map, and it will pop up the closest weather stations to the location that you clicked on. So again, I clicked on Leadville. I could use the Aspen one. I could use a couple of other locations around here. But yeah, I clicked on Leadville, and it's pretty good. What it will then give me for Leadville is this, annual heating, humidification, and ventilation design conditions. Same with the annual cooling, dehumidifications, and enthalpy design conditions. And you'll notice here the heating dry bulb, DB, dry bulb, that means it's going to change the thermostat temperature reading. Remember I said -8 for Leadville. That's right here at the 99.6, and -3 for Leadville would be the 99%. So you can use either one of these unless a code or permitting or program mandates that you use one over the other. For cooling, right, the 1% is 72.2. You just say 72 and 74. You can round up if you have to. 75 would be your cooling for Leadville. That's the difference between your 99% and your 99.6%. So this stuff is very important to understand where to find these details. They will be built into most Manual J software, but if you're using something that is only Manual J version 7 compliant, not version 8, you may want to, like I do, use this site, and then I will override in the software, and I will put in the actual numbers that I want to use, right? It might be the 99% or the 99.6%, and I'm going to use the 2021 numbers because it's probably going to be a little more accurate than if I had just let the software assume, particularly things that are only version 7, they may not be as up-to-date and accurate. So what all truly goes in? Remember, I talked about this earlier. We're going to get a little bit more details. Heating load inputs. The largest single load input for most houses is the envelope. So that's the square footage and the R and U values of the building. And that's UA times delta T. So it's the weighted U value of the area of your walls, your windows, your doors, your ceilings, your floors, times the delta T, the temperature difference between inside and outside. That's going to determine the largest single heating load for your building. Now, if I look across the country, the duct multiplier is the next highest. But in Colorado, or lots of parts of the upper Midwest where we have a lot of basements, I would actually say the ACH and ventilation in a cold climate may be the same or higher than the duct multiplier. So this is a funnel, again, depending, this is on a national level, this is true, but in our cold climates with basements, the ACH and ventilation may actually be a little bit higher than the duct multiplier. For ventilation, it's the cubic feet times the delta T times the air changes times 0.015, and that is a multiplier. It's 0.018 at sea level. When we get up to the higher elevations, it's much more common to use 0.015. This has to do with specific mass and gravity of air, right? Of course, it's going to be a little different with elevations. But those are the hardcore formulas there. With duct multipliers, there are some hardcore formulas, but most of the time we're making an educated guess, right? Because it's this duct multiplier is taking into account heat loss through the ducts, considering the insulation, the leakage, and the surface area. Now, I would say, that to a degree, when we were looking at gas furnaces, you only had to get so accurate because there were only 5 choices, and they ran from about 40,000 to 120,000 BTU, right? So, how accurate did you need to get? Well, just within this degree of range was probably good enough. But when we talk about heat pumps, there are 7 choices just between 1.5 tons and 5 tons. And there are some that actually go up above 5 to 5.4, and we're now getting pieces of equipment sold in, down to 1 or 1.25 ton. So we might even have as many, depending on the brand and the type, as many as 9 different choices for heat pumps. So it's almost double the choices. So this stuff getting more important to get this accurate because we're a lot more fine-tuned. We're also only going up to 5.4 tons. That's the equivalent of going to about 6,000 BTU on the other scale. So we may actually need multiple heat pumps within these range capabilities to do what we could have done with a single gas furnace before. So it does start to make sense to really get this information as accurate and as, again, reliable as we can. It's not about being perfect. Perfection is the enemy of the good. What we want to do is get that reliable and repeatable data. If we're talking about cooling, we have those same 7 kind of size options, up to 9 now. We might get 5.4 ton and 1 or 1.25 ton on the low end. Right? All of these are the same. The biggest difference here is that windows and solar or internal gains play a huge role in the cooling load. So windows, right? What's the U value, the solar heat gain coefficient? What kind of shading is there? And what is the orientation? Are the windows facing south or southwest or west? That's very different than the ones that face north. And then the internal gains, like the humans inside, how many people live in the house, plus all the stuff that we plug in, right? The televisions, the phone chargers, all of that good stuff. There's so many things we leave plugged into our home year-round. So just imagine the more detailed and restrictive the envelope gets, the more insulation and air sealing you have, the less your internal gains have an avenue to escape. So yes, you won't be losing and gaining heat traditionally as fast, but also the internal gains don't have anywhere to go. So it is really important with load calcs for cooling to understand that all of this stuff is going to factor in. So my rules for doing load calcs. I believe that you should use equipment or use tools rather that are Manual J version 7 or newer or equivalent or can give you the same answer. And so we'll talk about giving you the same answer in a little bit. So it's got to use the ASHRAE math from the ASHRAE Handbook of Fundamentals. Must be capable of being able to adjust on the cooling side for solar heat gain coefficient or adding low E glazing. Must be capable of doing heating and cooling loads, and must be capable of both block load and room by room. This is the balancing act we're shooting for. We want tools that can do all of this if possible. So what are some Manual J and equivalent approaches here? Now, if we're just talking software, the ones on the left, CoolCalc, RightSoft, Elite, Energy Gauge, Amply, Conduit Tech, there's others out there. Quick Model 3D I mentioned earlier. I didn't include that because that's effectively using the Energy Gauge calculations in the background. but there's several that are ACCA approved that are out there. And then there are ones like you see on the right, which are not ACCA approved, but they probably give very, very similar results. The HVAC sizing tool, it's free. It's Manual J7 equivalent. It does not have low EE glazing as an option, but you can adjust the solar heat gain coefficient, which helps you mimic that. The next one, LoopCAD and HeatCAD from the Canadians. They use a different set of standards, F280 instead of Manual J. It is not free, but I know people up near the border who sometimes use this software because they work across the border. And then H2X is a newer software to the United States. It's European. It started off as a hydronic sizing and selection software. It's getting its ACCA approval right now. It does have forced air in it. So it's a nice tool. And when it's ACCA Manual J approved, it can move over to the other side. So it's getting there. They're working on it. Anything on this screen is probably a pretty good piece of software to use. Now, when we're using desktop software, and most of them that I've mentioned so far are desktop software, except for Amply and Conduit Tech. Hold on to your hats. We'll get to them in a few minutes. But for all the desktop software, we're going to need to collect data in the field in order to put it into our software. So one of the things we want to do is have some sort of graphing paper so we can draw our houses out. You can actually download this if you don't feel like buying your own graph paper from my friends at Energy Vanguard. And what they talk about is there's going to be 3 things you need to do. You need to get a house drawing, you need to collect data, and then we need to make sure we've got proper locations and altitudes. So using the right winter and summer design temperatures. So when you draw this, it doesn't have to look as clean and sharp as the one on the left. That's great when they look like that, but the one on the right is also just fine. You notice it says which direction north is. This one they actually wrote down where the air handler is, the supplies and the returns. They identified all the windows. This is actually a pretty good way to do it. As long as you understand what it is you're looking at, this can be just fine to do. Now, very, very complicated, architecturally interesting houses, you need to take the time to be a little bit more detailed in your drawing probably. Some people will actually use laser tape measures to get more accurate, detailed information. That's great to do. If you just use a regular tape measure or a wheel walking tape measure, those can work as well. Again, the more complicated the house is, the more accurate it probably needs to be with those measurements. Then you want to start being able to record things like the description of the house, the blower door, if you got that number, then what type of insulation you have and where, what kind of doors you have, what kind of windows you have. If we're upgrading the equipment, potentially, are they looking at a heat pump? They're looking at multiple heat pumps, or they're looking at a gas furnace and air conditioner. Being able to record all this, as well as the mechanical ventilation, this is going to give us a lot of the features that will go into our desktop software. And then we get to our software. And while I'm showing the HVAC sizing tool, most of them are very similar in terms of their inputs that you need to do. So on the site, the number one thing I'm recording is the weather location, right? In the state here. Now, you see this thing for utilities. That's because in the Pacific Northwest, some utilities allow you to use this tool and submit it for their utility programs. You don't have to worry about that outside of the Northwest, but it is important you record the weather location, even though I may want to go in and override this using the ASHRAE design conditions. Then I would go to the building. Again, I put in the size of the house, the floors, the height, bedrooms, default insulation levels, what type of foundation, duct location, orientation, and year built. Every time I do it, I hit save. Then the rooms. In this case, I'm doing 3 block loads, or 1 block load for the building. I'm basically looking at the upstairs, the main floor, and the basement as my 3 rooms, right? This is a semi block load, semi room by room. This is my favorite way to do for most existing homes. It gives me that reasonable answer. It's repeatable. I'm feel fairly good about the accuracy of it. The only time I might not do this is if I have specific rooms with indoor air quality or comfort issues. But you can see here my score up in the right hand, and it changes as I hit save and I enter more data. Here I put in my windows. A couple things here, your window to floor area ratio, 16.6%. It will not have a green check if it's really low or really high. So there are some things built in so that you're sure, helping to ensure that you're not putting in absolute crazy numbers. Overrides. This would be a place where I could say I put in that baseline. I said 2x4 walls, not very well insulated, but maybe I know that they actually did blow the walls and insulate the attic at some point in time, right? Maybe they didn't do the floors yet, they didn't tighten the building up, or but I know that they did do some duct sealing. All this, I can put that in my overrides. I can go in on my options. Here's where I could override those winter and summer design temperatures outside and inside, the thermostat set points. I can override the ventilation, interior shading, my heating and cooling duct multipliers, right? All of these are additional pieces of information I can add or change to fine-tune my score. By the way, when should we do room by room versus block load? I can look at it this way. If I'm doing a new house or a house with significant envelope upgrades, or if I've got a retrofit and I've done an energy audit, I can do a room by room for both of those scenarios. It's going to be hard to do a room by room with a retrofit if I didn't do an energy audit, and the reason why is I need to know the square foot of each room. So if I haven't been to the house to actually do that level of information, I'm probably not going to be able to do room by room across the board. Runtime and bill analysis, I will need to have done some sort of energy audit. I'll need to have gotten either thermostat data or utility bill data for the homeowners. Block loads are good because I can do block loads with just some basic information, and I could do it in a new home or a retrofit with or without an energy audit, right? And again, I also might focus my room by room on homes with comfort and indoor air quality issues. Next up, we're going to walk through each of these, and I'm going to go a little bit more detailed into the amount of time and effort, as well as how accurate I think it is, right, and how recognized. So you notice my little hiker here is at the top of the highest peak. So this is kind of the premier. This is the best answer we're likely to get. For ducted homes, this is our most accurate, doing room by room. It does require the most time and effort, or it may require, there's a different approach where you pay a subscription service fee, but it's going to streamline your data entry and your reporting. It does require software training. It's very well recognized and aligns with codes and standards across the board. Block loads works great with homes that are ductless or simple homes. In most homes without indoor air quality and comfort issues, as long as I've got some decent data collection, block loads are going to work great for most of those homes. It provides total sizing, just not per room or per head. It still requires some software training and or recognized spreadsheet training, and you still need to get a lot of the basic home information. But the good news is you're still pretty high in the mountain range with your results here. The next one is using runtime to estimate the load. So this is, we're talking about a house with a smart thermostat, and being able to look back at the last full heating and full cooling season. It's better to have multiple heating and cooling seasons. The more data you have, the better, more accurate it will be. You need to know the local design temperatures. You need to know the efficiency of the heating and cooling system that was there. And you need to, again, if you only got 1 year of runtime data, you need to know, was that a typical year or an extra warm or extra cold year? If you have all of those pieces of information, and you can look and you can say, during the peak coldest days of winter, this thing ran 55 to 60 minutes an hour, you can feel pretty sure that it's pretty right-sized. If, however, during the coldest days and the hottest days of the year, the thing only ran for 35 minutes, you can be pretty sure it's well oversized. So that's using our runtime, right? So here we go, more detail. You need to have a smart thermostat, access to the historical data, A full heating and cooling season, multiple years is better. We use percent of the runtime to satisfy the thermostat during nights, similar to the winter design temperature, and days, similar to the summer design temperature. And I multiply that percentage of the hour by the output capacity of the existing equipment. If I had an 80,000 BTU system and it was 80% efficient, right, then I know that 3/4 of the BTUs that went in are what came out, so I know that it's 60,000 BTU out. If the thing ran for 30 minutes out of every hour, then I would multiply that 0.5, that's our percentage, times my 60,000. This tells me I probably only would have needed a 30,000 BTU system to run full time. That's our math. So can we base off our off our existing equipment? So not really, but maybe, right? So you may have a program that allows you to do this, and if so, we're going to put some parameters in here. The folks at Natural Resources Canada have determined that this is what they call their last resort for sizing. So if you don't have any other good way to do it, you can do this, and you divide your existing BTU output by 1.33 to get a more realistic size, right? So the asterisk is here is this is only if the house has no comfort issues and no one has done any weatherization or changed the envelope or added square footage since the last system was installed. If you meet these criteria, you can sort of do this based off of it. So you may recall very early on, we said that Natural Resources Canada identified these as being 125 to 140% oversized. We use 133 as the middle spot there. So if we don't have any other choice, we would get the existing capacities of the heating and cooling equipment. For the heating design load, we look at the output and 133% assumption of that's its size. So an 80% gas furnace rated at 60,000 BTUs would give us 48,000 BTU per hour delivered. If I divide it by 1.33 or take a third out of it, 32,000 is what I would have needed. Again, as a last resort, this is probably better than absolutely nothing, certainly better than just putting in what they had before. Now there's a bonus approach here, because I've mentioned this before, and there's a tool out there that I wish was available in more places. It's only available for Washington, Oregon, and California right now, and that's because it has some built-in lookups that will actually look up the rates over those periods of time. So it can look up historical rates as well as future rates, or current rates rather, not future rates. That'd be really impressive if it could look up your future rates. It looks up historical and current rates. But you can get an idea from the image from this group. If I know the home energy use at different outdoor temperatures throughout the year, I can estimate a load line, right? So my heating load and my cooling load can be estimated. I need at least one full heating season and one full cooling season. Again, multiple years are better, and we want to make sure that it was not an abnormally warm or cold year when we did that. You can do this. I have friends who have spreadsheets built out to do this, but the amount of time and effort it takes to do this, you could have just done a manual J. So there are some new kids on the block as well out here, right? This is Amply and Conduit Tech. I'm playing this little video here. You know you must be getting the big time when people are making TikToks of your tools, right? So Amply and Conduit Tech, they use the LiDAR functionality on an iPad Pro, and you go through and you quickly scan the house. It can actually, both of these can tell the difference between your walls and your furniture and your cabinetry, which is really kind of impressive. It, again, will generate a floor plan and a 3D model, and then within it there are these little pull downs once you've completed this. And you can assign each wall. That is a 2x6 wall, and it is insulated, right? That is a double pane window with a vinyl frame. When you do all this, it gets you pretty darn accurate. You can do the entire scan of a 2,200 square foot house in about 16, 17 minutes, and then another 5 to 10 minutes on the pull downs. Your whole manual J for existing home is done in under 30 minutes for the average size home. Now that is really impressive. These do come with a per month charge, So you really do want to make sure that you're doing enough load calculations a month to make this pencil out. Both of these are ACCA approved. I would generally say if you are doing 5 load calculations or more a month, this is worth it, because that just what the value of your time is worth, you will pay for yourself easily if you do 5 or more load calcs a month. If it's 4 or fewer, then it really comes down to the value you want to place on your time and the consistency, that repeatability and reasonableness you're looking for out of your software. You may decide that even if you do 3 or 4 load calcs a month, this is still worth it because the reasonableness and repeatableness are important to you, and you value your time high enough, put a high enough value in your time. So if you consider your time worth at least $75 an hour or more, then 3 or fewer is fine. So that's kind of some of the math you want to do here. These do use the ASHRAE math. They just streamline the data collection and give you really cool looking results. There's something else called Zero Homes out there. I left a link in here. It's a similar concept, but instead of you, the contractor, doing the load calc, the homeowner can go in and download software and do it. The difference is everything needs to go through the Zero Home program. So they actually do an energy advising phone call with the homeowner. They provide a bid and then give that assign contractors to those bids. So it's kind of a closed network program, but I do want to mention it because it does use some similar technology. It's also ACCA approved. So there are other ways to get there. I'm just mentioning this, lots of different ways to get there. I'm a big fan of Amply and Conduit Tech. And you'll notice that both of them are looking here about your HVAC sales, because boy, when you really can produce this level of detail and you have really great reports, this is a great way to help people see the value in what you're bringing to the table. So one thing people will say is, well, Dan, there has to be some rule of thumb out there. I mean, if you're saying that as a last chance we can size up the existing equipment, there's got to be some enhanced rule of thumb. So I will say, okay, let's take a look at an enhanced rule of thumb. You see that at least our little hiker is in the mountain range, right? So it's better than nothing. What I'm going to show you is an enhanced rule of thumb, probably okay for ductless heat pumps, if we're being honest. It doesn't really align with most programs and standards, and it may or may not be better than existing equipment. But what I'm going to tell you is if you use this correctly, I think that this is a tool that can be a good guide, but it is not a way to do a load calculation. So it's called the heating load estimator. You can see the very first thing it says is this is designed for rough estimations, for training, and for doing gut checks. By doing gut checks, I may mean if I'm a technician who goes out to a house and there's a no heat, no cool call, and I recognize that we can't save this equipment. I need to have a salesperson come out and size it. I could use this as a very quick way to say, hey boss, we need a salesperson down here, and I think that they're going to want, I think this system is oversized, and here's why. That's a good use of this tool. Another good use would be if you're trying to do load calculations and you're doing detailed load calculations for the first time truly, and you want to know, I don't even know if I'm getting close. You could use this as a reference to say, okay, I am within the right realm of sizing. So let's dive in and take a quick look at this. The first thing is, if you have a blower door test number, maybe either you did it or someone else has done it, but you need to translate this into the language that Manual J uses. Manual J says average, somewhat tight, or average, somewhat leaky. Well, heck, how do I know if a blower door number equals that? Well, the first tool here is you can look this up. If someone gave me a blower door test of 1,750 for this house, if this were a 1,500 square foot house, I would say, you know what? If I look at 1,700 where it meets 1,500, that is a somewhat leaky house. If, however, that building was 2,000 square feet and had a 1,750, I would say, okay, that's in the blue, that's an average house. If it was a 2,500 square foot house, however, it would be 0.7 right here in the green. I would say it's a somewhat tight house. So that's the first thing you can do, is use this part of the tool just to help translate a blower door number into somewhat tight, average, and somewhat leaky. So here we have our heating load estimator, gut checker, guesstimator, whatever you want to call it. There's several things in here. BTU hour per square foot, right? And there's 3 numbers within each block, and there are 4 blocks within each temperature range. So if I've got below -10 degrees as my winter design temperature, I could have a BTU per hour anywhere between 15 and 50, depending on if the house is leaky, average, or tight. Depending if, on average, there's no wall insulation, a 2x4 with some insulation, 2x6 with insulation, or newer construction, or super insulated, right? So I have that range in each of these temperatures, temperature bins. This allows me to do a lot of different things, right? To take into account where the house is, to take into account how insulated and air sealed it is, right? All of these, the size of the house, because we're doing BTU hours per square foot and multiplying by the square feet. So this is a enhanced rule of thumb tool that allows us that ability to fine tune a lot more than a standard. Again, we're not using this to replace a load calculation, but in order to check to see if the existing equipment is within realm of possibility, this might be a good tool, or if my only other choice is to size off of the existing equipment, or if I'm using a ductless heat pumps only. Those are the real good use cases for this. So I want you to look in this, I'm going to look at this 2x4 construction with insulation, and I'm going to look in the temperature bin of -10 to 5 degrees. You'll notice that I've got 3 BTU hour per square foot numbers I could use: 24, 22, and 20. 24 would be if I thought the house was leaky or somewhat leaky. If I thought the house was average in building tightness, I would go with 22. If I thought the house was somewhat tight or tight, I would use 20. Now this is the heat load estimator for a standard house. Next, we're going to look in the same box for a house with a basement. So here we have a house with a basement, and we're looking at the same box, right? 2x4 construction with insulation, -10 to 5. You notice my range is now 22 to 18. It got lower, that range did, and that's because we have less heat loss through the basement, because it's always, you know, somewhere between 47 and 51 degrees on that earth on the other side, as opposed to if the house were over a crawl space or something like that, where the crawl space temperature is going to be closer to the outdoor air temperature, which could be whatever the outdoor temperature is. So this is a enhanced rule of thumb, because now I've also given you the ability to look at this with basements. Next, we want to look, same thing, but what if we've got a lot of ductwork outside the envelope? So here we've got our heat load estimator with ducts outside the thermal envelope. I'm going to say if about 70, if we look at 70% or more of the ductwork is outside, heck, even 60%, this is probably the better tool to use. You notice now the same box, 2x4 construction with insulation in the temperature range of -10 to 5. I'm going from 26 to 22 as my range. Why? Now I'm even higher than I was with my standard, because ducts outside the envelope are going to have even greater heat loss and heat gain. So this tool provides you these 3 different mechanisms and different capabilities to give good ranges and estimation. So we're just going to do a quick guesstimate here. The home's 2x4 construction with insulation, no basement. So I use the basic version of the tool. The home tightness, we don't know. No one gave us a blower door test, anything like that. So the home is 2,000 square feet. We're hoping that they'll use a dual fuel hybrid heat pump. So I use the 99% winter design temperature of -2. My existing system is 60,000 BTU furnace. So projected range for this heating system would be between 48,000 and 40,000, and that's because I multiplied 24 and 20 by 2,000, right? That's my range because I didn't know my blower door number. That means our existing system is likely oversized. So if I'm that technician out on that no heat, no cool call, and I'm about to call the boss, and I'm about to say, I think we need a salesperson to come out, you can say, I think this one is a full ton or more oversized, right? That's how this tool works. I could do the same type of example, but maybe now I actually know the blower door number. Someone gave me at 1,750. So this is, again, I'm using, it's dual fuel, so I'm using the 99% winter design temperature, 29, I know it's 2,000 square feet. So I use that average tightness number here. My existing system in this house is 48,000 BTU. So if I do this test, right, it was an average amount of leakage. So use the average number, multiply 22,000 times, or 22 times 2,000, 44,000. 48,000 was the existing system. The heating load estimate was 44,000. I can tell the boss, I think the existing system is sized just fine for this house. This is how we choose to use this tool. Again, as a heat load tool, it's a frame of reference for us. If you have an all ductless house, very simple, no comfort problems. It probably is better than just sizing off of the existing equipment, but it is not designed to replace manual J. Next up, I want to address, does the envelope matter at all in these houses, right? I'm going to guess that you can guess what I think, but let me ask a couple questions. There's really considerations we should all take into account. Where is the end of your heating system distribution? Let's start with a ducted heat pump. Where is the end of the distribution system? Is it at all the registers and grills? Or does the heat that come out of those registers and grills, is it still warmer than the air temperature in the house? Well, the air temperature in your house during heating season is probably, around 70 degrees. The air coming out of those registers is going to be somewhere between typically 90 and 110 degrees. So yes, it's warmer. So that means that you're still putting warm air through. The actual end of your heating distribution system would be then the walls, ceilings, floors, windows, and doors. So when we think about weatherization, weatherizing our windows, doors, ceilings, floors, and doing building tightness is really just an extension of insulating our ducts, putting our ducts in good locations, and making sure our ducts are tight, because it's all part of the same distribution system. The next I'm going to ask, what determines human comfort? Now this is tricky because there's actually a long list of things that all contribute to human comfort, but what do you think matters the most? Now, if you are in a non-humid cooling climate, the answer is going to be mean radiant surface temperature. So Colorado, definitely. But anywhere else in the upper Midwest, during heating season, mean radiant surface temperature is going to matter the most. Air temperature, humidity, clothing, metabolism, yes, those all do contribute. But mean radiant surface temperature means kind of the average temperature of all the stuff around you. So if you've got some windows where that surface temperature is 52, some insulated walls, so the surface temperature there is 68, but a floor that's not insulated, and so the surface temperature there is 62, right? You've got inconsistent surface temperatures everywhere. You're going to have heat loss to greater degrees to all of those spaces. That is going to make it much more uncomfortable for you. On the other hand, a very well weatherized, yeah, the windows will still be a little lower than the walls because even a triple pane window isn't the same R value as a dense packed R15 wall. But you're going to get much less heat loss. You're going to get much more even surface temperatures. It's going to lead you to much greater comfort. So for people that prioritize comfort in their lives, guess what matters? Insulating, air sealing, windows, walls, ceilings, doors, floor, right? All of that is going to matter. And then let me ask you this last thing about when we think about, do envelopes matter? Do smaller heat pumps cost less? Now we talked earlier about getting right size heat pumps being important for a lot of reasons, we really haven't brought this up yet. Do you think a 3-ton heat pump costs less than a 4-ton heat pump? It sure does. By how much? Yeah, it depends on the brand, depends on the model and series, and it depends on what's available at your local shop. But yeah, smaller heat pumps typically cost less. So now let's go back to this and ask these questions again, knowing the answer. Our distribution system ends at our walls, ceilings, floors, windows, and doors. Those being consistent temperatures and being close to the air temperature or close to our body temperature means greater comfort. And if we can do this right and get a smaller size heat pump, we can save the homeowner money. So yeah, the envelope ought to matter to you because it certainly matters to the homeowner whether they know it or not. So why else should this matter to us? So sizing and selection and design, it's really dependent on the heating and cooling loads, and any retrofit that happens changes those loads. So it should matter to you because you're helping to drive this for the homeowners. The homeowners often need help in planning their retrofits over time. Now, utility incentives are great because you can stack them together, and there's often not a limit on, could you do insulation and HVAC and hot water, right, and new windows? Yeah, often you can. But with certain things like tax credits, there's a limit per year. So if someone wants to maximize tax credits, and they want to maximize utility incentives, and they want to get the best financing, they may need to stage things over time. And they're going to need someone to help them figure out how to do that. So perhaps doing a tune-up on the existing equipment to get it running again and doing the envelope first could get them some rebates right out of the gate, improve their comfort, maybe buy a little bit of time, and then next year maybe you can upgrade the HVAC system to the right size. And the homeowners will really value you giving them that benefit, right? So as we look at this, and remember, comfort isn't based on delivered air temperature and relative humidity alone. A lot of it's going to be based on the surface temperatures. So us getting this right helps those homeowners. Now, I've said that this in many trainings before, and there's still some truth to it, but we've said before, you need your envelope efficiency, your efficiency vegetables before you're allowed your mechanical proteins, and then you're allowed to have your renewable desserts, right? Kind of a joke, and we used to say this because the order of cost used to be that insulation was cheaper than equipment, which was cheaper than solar. But now we've seen solar come down, EV chargers come down in price, mechanicals are all over the place. Ductless heat pumps may be very affordable, and there can be some ducted systems that are extremely expensive. And then envelope efficiency, we've gotten more nuanced at it with windows and doors and insulation and air sealing and duct sealing. Different combinations can cost different amounts. So while we used to say it should happen in this order, and I still fundamentally believe that sizing things based on doing it in this order is going to be most helpful. First, control the envelope, aka control the comfort, then control the equipment. So now you have the defined load, defined capacities. Now you know how much solar you need or how much battery storage you need. So I still think that this is valuable, but the reasons that we used to say it this way are not. So now I want to kind of revisit this real quick because we want to look at the impact of some weatherization measures in a home. So let's start by looking at air sealing only. We're going to use the same box we've looked at a bunch of times before. We're going to say 2x4 construction with insulation. It's in the temperature range of -10 to 5, so we can think of a Pueblo home. We're going to start by saying, I think I didn't have a blower door beforehand, so I'm going to say the house is probably somewhat leaky, right? So I would use that 22 BTU hour per square foot and multiply it by the square footage of the house. If I multiply it by 1,600, that's a heating load of 35,200 BTU per hour. If I did some air sealing and I got it to somewhat tight, I could do the same math but go from my 1,600 square feet to 18 BTUs per hour per square foot, and that's 28,800. Right? When we do that, I look at this and say, I changed my heating load by almost a half a ton just by air sealing in this house, right? So doing air sealing by itself gave me a 1/2 ton benefit. What if I wanted to do some insulation as well as air sealing, right? So now we've done some insulation and some air sealing. I'm going to use the top box still and say that this is equivalent to a 2x4 house with some insulation, but after I've air sealed and insulated, it's kind of performing more like a 2x6 house with some insulation. This is, again, just a rough guesstimate just to show you this. So I would go ahead and use the central numbers here, just so I can have a single number and say my starting point might be 20 BTUs per square foot. That's 32,000 for the house. After weatherizing, it changes down to 13 BTUs per square foot. So that's 20,800. So going this way, I've gotten almost a ton of heat load reduction by weatherizing. So air sealing alone got me almost a 1/2 ton, a little more than a 1/2 ton. Full insulation got me more like a full ton. A different way to say this is if you do air sealing and insulation together, you're usually going to get a ton to a 1.25 tons reduction on your building heating load. So do you tell me, will that relate to a smaller piece of equipment? The answer is very possibly. I could very possibly put in a smaller piece of equipment if I air sealed and insulated. Will my bills be lower if I have a much lower heating load in my house? Yes, they will be. So now a smaller piece of equipment, smaller bills. Will I be able to control my mean radiant surface temperature with air sealing and insulation? Yes, I absolutely can. So my comfort can go up, my bills can go down, and my first cost of a new piece of equipment can go down, all because of insulation and air sealing. So this was just using this tool as a way to estimate it. There are other things that can be done. Energy modeling software is a really good way to look at this as well. In Minnesota, my team did this research along with some others, and the idea was we were looking at our baseline building stock. We had done a building stock assessment for a potential study for the state of Minnesota back in 2019. So we understood pretty well what the average homes looked like in Minnesota. And we looked at them as they were and said, how many of them could be satisfied with a heat pump, with knowing what the 2020 quality of heat pumps looked like in terms of their capacity, their efficiency, right? And so we said, well, let's model a fictional CO2 5-ton space conditioning heat pump. We're going to model a real-world high-end 5-ton one. We're going to do a real-world high-end 3-ton. We'll do a reference 5-ton and a reference 3-ton, meaning kind of just out of the box or most average. On the left of the two bars, this is the baseline building stock, and then the right bar next to it is if we did a full weatherization package. And we just started by looking at pre-1990 homes. So the homes where weatherization would likely benefit them the most. If we look at these and said, let's use the fictional one is great. If we weatherize these homes, fictional ones could do 100% of it. But let's look at the real high-end systems. And the high-end 5-ton, high-end 3-ton, and reference 5-ton. If we look at the high-end 5-ton, after weatherization, we changed from being able to address about 42% of the pre-1990 homes to closer to 75% of them could be handled by a heat pump at 5-ton. It means, yeah, there might be some that need more than that, but that is a huge improvement. How about if we looked at the high-end 3-ton system, right? We go from about 15% to about 42% of pre-1990 homes can be addressed with that 3-ton, or 3-ton system. What about the reference 5-ton? So we're not even going with the high-end one. We can do 33% of the pre-1990 homes that have been weatherized with that. So that is big news, right? We saw this as a different way to look at it. Instead of saying how much lower the heating load will be in a home, we're looking at how many more homes can be treated with heat pumps because of weatherization. And for our utility friends, we also noticed that when we looked at these, We also saw a 25% peak load reduction by doing weatherization. So you have an option as a utility. You can either have if peak load is a huge component for you, you can either look for pieces of equipment with a high EER2, an EER2 rating, which is loosely translates in some ways to peak load conditions for systems. But you can also look at things like you could just recommend or encourage or require weatherization, and you get all those additional benefits and those peak load reductions. So we see this as very important reasons why we want to think about this. So all of that said, if you're an HVAC contractor and you don't do a lot of this, it's still probably worth asking the single couple of questions here of a homeowner. If you just started doing this, I think this would be a great place to start. Just start by asking this one question. Mr. and Mrs. Johnson, Mr. and Mr. Smith, are you willing to weatherize your house, right? Are you considering it? Are you willing to do that? Or winterize it, or insulate it, or air seal it, whatever terms they like to use. Now, there are a bunch of different types of answers. I'm going to give you 3 very predictable answers. With each one of these, there's a potential way that you could address this. So we start by saying, this is, what should we discuss and do in response? So the first thing they might say is, no, this is an emergency replacement. Fair enough, right? They haven't thought about weatherization, not on their radar. The thing just broke. They just need to get the heating and cooling working again. Okay, can we design and install a heat pump that is flexible enough so that when they do eventually want to do this and they have lower loads in the future, the equipment can still deliver? We're going to talk a lot more about this in the second recorded seminar, because that one we're talking about sizing and selecting equipment to meet the needs of the home. So we could look at systems with what's called great turn down ratios and very wide Goldilocks zones. So really capable of load matching that are right sized would give us the most flexibility to put that in now so that a home gets weatherized in the future, the heat pump still works. Maybe they say, yeah, I'm very interested in, sure, I love the idea of better comfort and lower bills and right-sized mechanical systems. Awesome. So in this case, it's probably best we install the heat pump at the same time or after weatherization has been completed. So one thing that can be done is you can redo the load calculation with assumptions that the air sealing will be reduced and the insulation will be increased. So you're actually sizing it if you install it at the same time as weatherization, a slightly smaller piece of equipment, or you can have the weatherization done first and then do it if the system is not completely broken. There are some utilities like Xcel Energy that will actually offer you a bonus incentive if the heat pump is installed within 6 months of doing the weatherization. Why? They believe in this type of prioritization equals success. And then you may have homeowners like, I'm just not sure, right? This sounds good, but I want to do more research. Maybe I want to talk to someone who can talk to me about pricing for weatherization. And if you're an HVAC, that's maybe not you. That's okay, you're going to get that. So maybe in that case, you can introduce these folks to a weatherization contractor. So if you get to know even a couple of weatherization contractors who can help have this conversation with homeowners, I want you to just think about, what do you think, how does this reflect on you if you take this approach with the homeowner? Say, I'm just looking out both for your current needs and your future needs, and I want to make sure we do right by you. And this is how we've thought this stuff through. Do you tell me, does this make your business look better? I believe that it does. So what did we cover today? We talked about the sizing methods to complete accurate load calculations, right? We talked about the risks of oversizing and doing low quality load calculations. We talked about the value on the other side of high quality load calculations, what that brings. And we talked about the tools we're most likely to use. All of this was really important. I really hope that you had a great time with this. I hope it all made sense to you. As predicted, we came in just under 2 hours. If you need to, you can reach out to me at the content information on the screen, or you can try to find me on LinkedIn. That's another great way to get a hold of me. With that, I want to say thank you very much for spending your time with me today. I know how valuable and important your time is. It was worth it for me. I hope it was worth it for you. Thank you all very much. Go out there and right size.